Welcome to Spring LIB.
For this problem, we are told that the force on a particle is given by F equals negative k r of t, where r of t is the path that the particle is following. We are then asked to write and solve the differential equations for each component, where r of 0 equals 0 and r prime of 0 equals 2j plus k. So, writing down the differential equations, we'd have that, important detail, the particle has a mass m. So, we'd have then that m times a, because force equals mass times acceleration, but acceleration is second time derivative of r, so we'd have that m times r double prime of t, I'll call that rx double prime of t, equals negative k rx of t. Oops, that's an f. Negative k rx of t, m ry double prime of t equals negative k ry prime or ry of t, and mrz double prime of t equals negative k rz of t. Then, when we want to start solving these, we note that all of them have the exact same sort of form, where they are second order differential equations. So we make the substitution that r, x, y, or z, I'm just going to write it as r, equals e to the power of mx. So we'll, or actually I'll have to use something else. Let's call it n, e to the power of nx. But actually that should be e to the power of nt, because t is our independent variable here. So we'll have m times t squared equals negative k times nothing. So just mt squared equals negative k, which means that t squared has to equal negative k over m, which then means that we have t equals plus or minus I root k over m, which when we substitute that into our equation for r, and I'll write rx equals ry equals rz, they will all equal, well, e to the power of I root k over m plus e to the power of negative I root k over m. That is going to be the form where we get a combination of cosine and sine as the solution. Specifically, we'll have that rx, ry, and rz will equal c1 times cos of root k over m, root k over m t, plus c2 sine of root k over mt. Oops, that was a big blurry k, but anyways. But we'll note that that we have different parameters for each one of those differential equations. So now that we have that, we want to actually solve for the given components or given conditions. So we'd have that rx of 0 needs to equal 0, and that is going to equal c1 times cos of 0, so that is going to equal c1. So we have, or c1x, so we have c1x equals 0, and we have r prime x of 0 is equal to 0. So we'd have then that would also equal, oh, actually, oh, no, never mind. So that would equal, when we differentiate everything, we'd get that root k over m. Actually, I'll write this out explicitly rather than just talking it through. So we'd have that is going to equal root k over m times cos of root k over mt. So that's just going to equal root k over m times c2x. And we can see then that we have that c2x equals 0. So we'll have nothing, excuse me, that came out weird. We'll have nothing in the x component. Then we want to go through and repeat the process for ry and rz. So I'm going to pause and do that off screen here. So we'd have that by the same logic as previously, ry, or we'd get that c1y and c1z would both equal 0. Then we'll have something different for c2 though. Keep in mind that for any of our things, we'd have that r prime of t, especially knowing that c1 is going to be 0, we'd have that r prime of t would equal root k over m times cos of root k over m, or excuse me, root k over m c2 times cos of root k over m t. So we'd have that ry prime of 0, that must equal 2 from our initial condition, which in turn must equal c2 times the square root of k over m, or c2y, I should say, times the square root of root k over m, which means that we have that c2y equals 2 root m over k. And similarly for z, r prime of 0 is going to equal just 1, which is going to imply then that c2z must equal the square root of m over k. So we can now say that the solution is going to be that r vector of t is going to equal nothing in the I component, then 2 root m over k sine of root k over m t j hat plus root m over k times sine of root k over m t k hat.